Hello, everybody. Today, I'm going to talk about TinyML as a service. And here's today's agenda. First, who am I? I'm a researcher in Ericsson in Finland. I used to be a Linux ARM kernel contributor, and especially working for TiOMAP and NVIDIA Kevlar. But recently, I have been doing completely different things. So, what is TinyML? The definition of TinyML is running machine learning inference on ultra low power microcontroller. But this looks a bit vague, and this is only hardware perspective. So our interpretation of TinyML is like this. So you see here, there are three technological areas: Linux, machine learning, and IoT, component IoT. And historically, the overlapping area of Linux and IoT is embedded Linux. And recently, most of the machine learning is happening on cloud. It's a training phase. And machine learning inference is happening in this area, edge computing. But there is another area, IoT, machine learning, but a device which Linux cannot run. So this is the area, TinyML. And this is the hardest part, because all the pain starts when Linux cannot run. So this is our definition of TinyML. So why edge computing is not enough? So this is a spectrum of the computing, and it started from cloud to compute edge and device edge and sensor. So proceeding with the sensor, resources are getting more constrained. But as you see here, 90% of the data coming from the sensors. But nowadays, those data are not processed efficiently because it has to be escalated to the above layer. And also, sensor devices can be a battery power. So battery consumption is a problem. As you see here, transmitting data consumes more energy than computer in place. So it's better not to sending a raw data, but a process in place locally. And the advantage of that is, if you look at this, this is traditional IoT. So camera is working, and the camera just sends the exact same raw image to the cloud, and it's processing in the cloud. And this requires strong connectivity, high bandwidth. But in this case, if you put the machine learning running on camera sensor, then the metadata, after process, metadata is quite small, and it can save the bandwidth. And also, it means that it's a battery, and it's a metadata, so it doesn't require, doesn't include any private data. So the privacy is preserved. There are quite good things. And also, the current boom of machine learning comes from deep neural network. But the problem is DNA model is too big to run on a variety of constrained IoT devices. So look at this. This is the TVM, one of the implementation of machine learning compiler, and it's software stack. So there are multiple machine learning frameworks. They didn't have the compatibility in the past, but now with the introduction of NNX open neural network exchange format, training and inference can be executed in different frameworks. So training can be done in one framework, but inference run on any framework. But still, this has solved one problem. The another aspect is diversity of the hardware. We have quite many hardware and hundreds of AI chips are coming. And any single framework can support everything. And also, typical Python-based framework is too big to run on such constrained devices. So where the machine learning compiler is needed. So technically, machine learning compiler is the key enabler of TinyML. Then, what is TinyML as a service? So this is our answer towards the emerging TinyML technology for the connectivity supplier. So there is a huge gap between the development experience between the web and embedded. Web it has a 64-bit of CPU and with gigabyte of memory and terabyte of storage, and the OS is Linux with container virtualization. On the other hand, embedded one, it has a variety of microcontrollers are used with at most half megabyte of SRAM, a few megabytes of flash memory, and variety of real-time OS, and there is no virtualization at all. And the situation gets worse when machine learning environment. Because machine learning is started with the training in the cloud and with big GPU, and after it's trained, still it cannot fit in any machine learning framework cannot run on such embedded area. So to solve this situation, what is needed is customization. So we need to customize the machine learning models to fitting into the device you use. So which means that it's like a pizza online. You need to specify what kind of topping is needed and what kind of base is needed. So this kind of customization service is needed. So this is the steps we need in the TinyML as a service. So at the first, you need to know device information. Then to find the appropriate machine learning model for that service. And that model has to be squashed into fitting into the device you run. But this is not only about the model, but you need to tune the runtime as well, because general purpose runtime is too big to run on the device. And build image for the operating system to run on, and it has to be orchestrated on the device. So those 6 steps are needed for TinyML as a service. Then, what does it look like? Look at this. Training, we assume training is done on the cloud, and trained model is stored in a model in the cloud. And this model cannot be run on this device directly because it's too big, and also the diversity of the hardware environment. So as a customization service, we propose TinyML as a charge. And it's backed by the multiple machine learning compilers because diversity of AI chips. So first, it collects the information from the device and download the model and compile it and appropriate image. And it's going to be orchestrated and installed. That's how TinyML as a service works. And so far, we need to support multiple backends, like multiple compilers. So we we expect the backend is provided as a Docker image. It's like a function as a service. So the front end just calls the Docker API to run on, like compiling, installing, as such. And for orchestration protocol, we are currently using lightweight NPM. It doesn't have to be lightweight NPM, but this is so suitable for us right now. And this is one of the popular IoT protocols. It can export the feature of the devices in a standard manner. Also, this protocol supports SOTA and FOTA. And FOTA is a firmware over-the-air update. SOTA is software over-the-air update. So what it is, the difference is FOTA is full update, and SOTA is partial update. Of course, partial update is preferable for us because it can save the bandwidth of the network, and it eventually saves battery. And this has supported in a standard manner. That is the good point. And TinyML service is front end is API server. So it provides the REST API to against the objects like devices, and the devices is associated with compiler, inference, and the installer. And if you host then each backend, it's trigger. And usually, IoT platform has orchestration, service orchestration mechanism. So with that, TinyML service can make use of that kind of existing infrastructure. So TinyML service can be optionally integrated into the existing IoT platform, and it can accommodate multiple machine learning compilers. So this is the TinyML as a service which we are working on. So then next is the ecosystem. So what is why ecosystem is needed for us? Look at this. One company, as you see here, we have the multiple backends here. So any single company cannot support everything by ourselves. And we need to collaborate. To collaborate efficiently, we need to specify standard interface for ecosystem. And currently, I'm considering those three interfaces: compiler plugin, orchestration, and inference module. And I'm looking at one by one. So first, compiler plugin. The model is downloaded and it's compiled in the TinyML service. But as I said, multiple compiler has to be supported. So which means that it's better to specify this plugin interface. But what the interface means here? So it can be categorized into two, input and output. So the input is the device information, how much RAM, is available, and also what kind of hardware accelerator each device has. And of course, machine learning model has to be passed to the compiler. And how much quantization is needed, because quantization is sacrificing the accuracy. And in return, machine learning compiler will return the compiled module. It's a smaller version of model with specialized lambda, because developer path runtime is too big. So that has to be combined. So this is the compiler plugin. The next one is orchestration protocol. So at first, it needs to take the device info from a device, and based on that information, this module is generated, and this module has to be passed to the device. So far, standard lightweight MTM, sorter and footer and its object is enough for us. We don't do anything more than that. And as I said, sorter is more preferred because drive update, partial drive update, and the amount of size to transfer can be saved. Also, even the device does not support lightweight MTM, we have some workaround. You can insert dummy lightweight MTM and to pretend as if device is a lightweight MTM. But on the back end, it can do this kind of flashing. So this can be used as a transitional purpose or even some product use case as well. And the last interface is module format. SOTA, lightweight MTM SOTA specifies the only protocol, and how the binary is installed, updated, is depends on implementation. But in IoT, there are many real-time OSs. But if this module format is OS agnostic, then we can save recompilation, and the same module can be used for over multiple real-time OS. That is very convenient. It's saving the effort. And I see there are three profiles. And the first one is general purpose, quite a rich environment, and second is embedded, and the least one is a bare metal. For the general environment, like Raspberry Pi, even Linux runs, then Onyx plus Onyx runtime is enough. And for bare metal case, you don't have any other choice than full flash. But for the embedded case, you can use SOTA and save the transfer with this module format. And this has this kind of benefit. So those are the interface I'm looking at. And for if you use lightweight MTM, you don't do much things, but the rest of the interface has to be standardized and specified. And we cannot do it all by ourselves. That's why we are looking for ecosystem partners to specify those three interfaces, like AI chip vendors, machine learning compiler vendors, and IoT device manufacturers. Also, service providers are welcome. Piloting to prove TinyML as a service is useful on their business field. Okay, and I forget to mention about the some talk we did. Okay, for the TinyML, we did last year proof of concept with Unikernel and Ocaml, and this was presented in the embedded Linux conference last year, and you can get all the information from this site. And there are slides. It's 72 slides. It describes quite well about what I did for in those slides. So if you are interested, please take a look at this one. And this year, I'm working on this narrowband IoT use cases with this kind of devices. And if after we get some results, I also want to publish this result too. And also, we have published those three articles. So what is TinyML as a service, and why TinyML as a service is needed, and how it can be implemented. So if you are interested, look at this one. And also we published the article about the TinyML as a service in IEEE, the IoT newsletter as well. So there's a link. So if you are interested, please go ahead to do that one. So summary, we are looking for partners. One is the ecosystem partner to specify those three interfaces: compiler plugins and orchestration protocols and inference module format. And we are quite welcome. We would be very happy if you can collaborate on that area. Also for piloting partners to validate TinyML service in their fields. So the left side is traditional edge-based, cloud-based IoT, and like one is the TinyML as a base one. So this one, you have green sensors send raw data to the gateway, and the gateway just sends raw data to a cloud, and all the intelligence are running on cloud. This requires strong connectivity, and this is not flexible, and this requires a lot of investment. So compared with this, TinyML-based solution, raw data sent from sensors are processed on this microcontroller in place locally, and this does not require a strong connectivity, but a narrow band would be enough. And this is quite flexible and save some kind of investment at the first stage. So, for example, if you are looking for predictive maintenance, like if you want to know when the time to replace the component before it gets broken, then TinyML is one of the options, because operation downtime is so expensive. Also, if your shipped products are deployed on a wider field, which the normal network like Wi-Fi cannot be placed, then narrowband IoT can help as well. And in that case, battery power is so precious as well. So if you are interested in such collaboration, please contact me, and we are happy to collaborate with such collaboration. And thanks for listening.
Thank you, Hiroshi. There's a couple of questions in chat, if you could answer them, please.
For the question is license information in the model format. We haven't thought about that attribute, but it can be achievable over any attribute of the model. But we are more thinking about the binary module format in a lower layer. But of course, it's possible. Yes, so the question, next question is definition of constrained IoT. There's some specification in the IETF, but in brutally say, I mean the non-Linux environment, like ARM Cortex-M CPU. So as I said, as long as the Linux runs, similar solution in the cloud can be applied, but all the pains start when the Linux cannot fit in